Hey folks, welcome to this episode on external effects on equilibrium and Le Chatelier's principle. So there are a lot of factors that affect the position of the equilibrium. Such factors are concentration, pressure, temperature, and catalyst. And these are what we call stresses. Now, these stresses, they can actually change the dynamics of an equilibrium system or a system at equilibrium and push it either one way or another, push it towards the product side or push it to the reactant side. What the principle, Le Chatelier's principle, says is that when a system is in equilibrium and it's subject to some kind of stress or change, the equilibrium will shift so that it counteracts that change. Basically, it's going to try to undo whatever has been done. So if something, for example, is removed from a system in equilibrium, the system is going to shift either left to right or reactants or product side so that it replaces whatever was removed. If something is added, the equilibrium will shift to use up whatever was added in that case. So again, it's going to try to undo whatever was done. Now, generally what we see is that a system that's in equilibrium will already have some kind of established equilibrium. Once we put a stress onto that, what's going to happen initially is you're going to have a non-equilibrium state. So it's going to push it out of equilibrium, but then the system is going to try to shift and establish a brand new equilibrium. So you might see a drastic change in either concentration, pressure, etc. initially, but then there's going to be a shift to establish a new equilibrium. And again, this just means that the forward reaction or the reverse reaction is going to go faster initially to either use up or replace what has been removed in order to establish a new equilibrium shift. So let's look at concentration first. If we look at the following example here, where we have NO plus CO2 gives us NOCl, you can also see that this is an exothermic reaction, and it's an equilibrium, reverse reaction over here. Now, if the concentration of Cl2 is increased, which way is it going to shift? Well, if we think about it this way, Cl2, if we increase, and assuming there's a lot of NO as well, if we increase more Cl2, that means we're going to have increased number of collisions between Cl2 and NO. Increased number of collisions means more chance of an effective collision, meaning that the forward rate is going to go a lot faster. So initially what we're going to have is, as we add this, our equilibrium is going to shift really, really hard to the right to produce more NOCl. Now eventually, as we create more NOCl, the reverse reaction is also going to increase at the same time that the forward reaction is decreasing. As we convert the Cl2 that we added into NOCl, that forward reaction is going to decrease. So we had an initial initial high rate of reaction in the forward direction. That created a rate of reaction in the reverse direction to be a little bit higher, and slowing that at the same time. Eventually, what's going to happen is that both reactions in the forward and the reverse are going to come to the same speed, and at that point, we're going to have our new equilibrium. And that's what we can see over here. This is our existing equilibrium over here, and that could have existed for a while. It doesn't really matter. But at this point right here, we see that we have an introduction of Cl2. That creates a spike in this concentration of Cl2. And what you notice is that from that spike, the equilibrium the reaction in the forward direction has increased to use up that Cl2, where you see our concentration is going back down. Now, at the same time, our concentration of NO is also going to be going back down. Now, it's twice as much because it's a factor of 2. But what we see is that we've established a brand new equilibrium. You can see that was our original equilibrium. This is our new one. Same thing here. So we've established a brand new one, and that's going to be going on from here on out. But you can see that initial spike. This is our existing. This is our stress. This is our response to the stress. And this is our brand new equilibrium at this time over here. So like we saw it over here, there was the same thing that we just said. As we increase more Cl2 or even increase more NO, we increase collisions, which means our rate of reaction in the forward direction is going to be increased. Then as more NOCl is produced, we have that large increase or that rapid rate of reaction over here, that instantaneous rate here as it slows down. The slowing down is caused by this NOCl starting to rebound with each other and create more of the original reactants. Eventually, as our concentrations of this and this go down, those rates start to plateau, and eventually we reach a point where the forward reaction is equal to the reverse reaction, and we get a new equilibrium. So one little note here is that in this case, the position of the equilibrium changes. It's going to lie a little bit more to your right, where you're going to have more products. So initially, it might have lied somewhere in the middle, but now as we've increased the Cl, we're lying more to the right. So the position of the equilibrium changes, but the K equilibrium doesn't change. The value of the K equilibrium remains constant for concentration, for pressure, for surface area. The only thing that changes the value of K equilibrium is temperature, and we're going to be talking about that a little bit later. So the reason that K equilibrium stays the same is that even though equilibrium lies somewhere else, the relative ratios between the products and the reactants is the same. So pressure, when we talk about pressure, we look at the partial pressure of the gases, and in this case, we can pretty much do the same thing as increasing the concentration. Now, to increase pressure, we can obviously increase pressure, we can add more moles, or we can decrease the volume of the container. So remember that when we look at concentration, N is over V, C is equal to N over V, if we change our volume, we are going to be effectively changing our concentration. And that's how this pressure and the concentration kind of work together. Now, as we decrease our volume, we're increasing our pressure, meaning that all the partial pressures of all of the gases are going to be increased. So if we had a system that was in here and we have all these little gases here, and we decrease the volume, we still have the same amount of gases, but they're closer together. Okay? And it doesn't matter if we have some reactant gases, the black dots are the products, the blue dots are the reactants. The pressure of all the gases, of both the reactants and the products, is going to increase. Now, the way that the equilibrium is going to shift is it wants to reduce this pressure. As we change our volume from our initial condition here to here, we've created a huge spike in pressure. The system wants to bring down that pressure to somewhere near its original value. It's not going to be its original value because we've dramatically changed the volume, but somewhere nearby. Now, the way that it can do that is by reducing the number of moles. We said that either the change in volume or the change in moles is going to affect the pressure. If we have less moles here, then that means we're going to have less particles hitting the edges of the container, which means less pressure. So the equilibrium will shift to the side that has the fewest number of moles of gas present. So what do we mean by that? Is if we had A plus B, and we had, let me just do that, a two-way arrow here, and we had an equilibrium system, and we had 3C. So on this side over here, we actually have 1 plus 1, we have 2 moles in total, and on this side, we have 3 moles of C in total as well. So in this case, if we were to decrease the pressure, or increase the pressure by decreasing the volume, we would see a shift from right to left. We'd go from products to reactants, because we have less moles on this side. Less moles means less pressure, and that's exactly what the system wants to do. It wants to bring it back down to somewhere near its original value. All right, so in this case, again, what's going to happen is that as we go here, as we have in this reaction here, we have 2 plus 1. On this side, we have 3 moles in total. Here we have 2 moles. So if we see an increase in pressure, we're going to see an increase in pressure in all of these species over here. However, it's going to move in the direction that produces the least amount of moles. And in this case, that's this side over here. So we're going to move from here into here and create this. Now, when we look at this, decreasing the volume, what it essentially does is it causes more collisions between the particles in both directions. So the forward rate and the reverse rate are also increasing. When we look at this, as the product accumulates, the reverse reaction increases until all the rates equal a new equilibrium. So we will have something here, but again, equilibrium will lie closer to this side over here because we're producing least amount of particles. So here's an example. In this example, we have 2 gases in this syringe over here. We have a combination of N2O4 and NO2. Now, you can see that it's a combination of these 2 gases because N2O4 by itself is a colorless gas. NO2 is a deep brown gas. So if we have something that looks like this, it's not completely deep brown, it's not completely colors, it's a mixture. And right here, what we have is we have an established equilibrium. Okay, so we've let this reaction take place, and this is where the equilibrium lies right now. It's some kind of combination between this and this. Now, from here to here, from step A to step B, what you can see is that the volume has been reduced by half. So the pressure has also increased twofold, and that goes back down to Boyle's law. If we see here, or when we look at this over here, we can see that the color has changed. Now, the reason that the color has changed is because we've rapidly decreased the volume, meaning that we've increased the concentrations of both. Remember, going back to C is equal to N over V, when we look at our concentration, our moles have stayed the same, but our volume has decreased. So effectively, what we've done is we've increased the concentration of each gas there. And that also means that we've increased the pressure of each gas. We've increased the partial pressure of each gas there. Now, what's going to happen is, again, this system, if we look at a graph in terms of pressure, pressure may have been here for step A, and then as we decrease the volume, the pressure has increased. Okay, and that would be step B. What the system wants to do is it wants to try to reduce that pressure to almost original circumstances. Now, the way it can do that is, again, if we look at this side of the reaction only has 1 mole, this side has 2. And so what we'll see is that we'll see a shift going from the product side into the reactant side, creating more N2O4. And you can see that by the color here. This is after the equilibrium has shifted and a new equilibrium has been established. You can see that the color is a lot lighter than this color over here because most of the NO2 that's been reacting has now gone into forming N2O4. Again, as we decrease the volume, we're increasing the pressure, and that also brings these particles together closer. Closer particles together means more collisions, means more effective collisions, and more conversion into N2O4, because that rate of reaction in reverse would be a lot faster. So the color shows us that this is actually happening. It's validating Le Chatelier's principle of what the shift is predicted to do. So once again, from here to here, we see a difference in color change because our equilibrium is shifting from the side that has more moles into the side that has less moles. The side that has less moles is more colorless, and that's why we see a little bit of a lighter color. Now, going on to temperature. In this case, remember going back to energetics into our enthalpy studies, and we saw that one of the ways of expressing enthalpy is by including it as a term in a thermochemical equation. Now, in this case, when we look at this 76 kilojoules, it's on the product side, which means that it is an exothermic reaction. If we had this heat on this side of the equation, it would be treated as a reactant and therefore an endothermic reaction. So in this case, what's going to happen is that in this exothermic reaction, if the temperature was decreased, what would happen would that the system would try to make more heat. It would shift in the side to make more heat. So in that case, it would actually shift to the right. So we can treat energy as an actual reactant or a product. If we add more heat, in this case, so if we're looking at an exothermic reaction, if we added more heat, aka this reaction would try to use up the heat and it would go into the reverse reaction. If we removed heat from here, then it would try to recreate that heat. Now, for an endothermic reaction, the opposite is true. If we were talking about an endothermic reaction, the heat was over here. Well, if we added more, then it would go in the forward direction. If we removed heat, it would go back into the reverse direction. And one note about temperature is that if we cool down the system, we actually reduce both rates of reaction. Remember that if we reduce the temperature, our kinetic energy is also decreasing. Less kinetic energy means less forceful collisions, and if we go back to our Maxwell-Boltzmann distribution, okay, what that means is that we're going to have less particles with enough energy to overcome the activation energy. So we are reducing the reaction rates in both sides. However, the key part here is that if we have an exothermic reaction, if we go back and look at our thing, we have 2NO plus Cl2, and that's reverse forward, and that gives us 2NOCl plus 76 kilojoules. Even though we're slowing both of these rates down, the rate in the reverse direction is even slower, because if we're removing that heat here, it has less heat to not only go back and get back the enthalpy change, but also then overcome the activation energy in the reverse direction. So when we remove this heat, that reverse direction is going to be a lot more slower. So eventually what's going to happen is that the rates are unequal, and that forward direction is going to be a lot bigger, okay, than that reverse direction, and it's going to initially favor the forward reaction, creating more NOCl, and at the same time increasing the amount of heat. So once again, if we remove that heat, that forward direction is going to be favored to produce more heat and also at the same time produce more of this other reactant. So eventually what we're going to have is, at the end of this, whenever it's established a new equilibrium, we're going to have a lot more product than we had reactant. And that's because we have this uneven rate of reaction. Now, because of this, we actually change our K equilibrium value. And this is why temperature is the only one that actually changes this. It's this unequal distribution of the rates. So again, temperature and KEQ, it's the only thing that will actually change the value of KEQ. The reason that is that when you change this, you're not changing the number of molecules that are reacting. When we increase concentration, for example, we're increasing moles. Or if we decrease volume to increase pressure, we're increasing the moles relatively compared to what we had before. And so when we're changing the temperature, we're not changing any amounts of the molecules. What we're doing is simply increasing the rates. And so what we'll end up with is a disproportional, maybe not disproportional, but a different proportion of product to reactants at the end of it, causing a different KEQ. So if you don't remember how this looks like, if we simplified our reactants and our products, and here's our thermochemical equation, this being an exothermic reaction, remember that our KEQ is determined by the concentration of our products over our reactants. Now, if we are looking at an exothermic reaction and we increase the temperature, what that means is that here's our exothermic reaction, we increase our temperature, we're going to try to shift in a way to use up that temperature. So the reverse reaction will have more heat, more energy to go into that reverse reaction, and will produce more reactants. So our ratio between products and reactants is going to be a lot different than what we originally had. We're going to have a lot less products than reactants, and our K value is going to decrease. Now, flip side, if we had an endothermic reaction and we increase the temperature, so an endothermic reaction would be reactants plus heat would give us products. So if we increase the temperature, well, that means that we would be fueling the forward direction and would create more products than we have reactants. And again, in that case, that would affect our K value. Our K value would increase. Now, the last factor here is catalysts. Catalysts just allow the reaction to achieve equilibrium faster, because they actually increase the rate of the forward and reverse reactions equally. They do this by offering that lower activation energy. Now again, remember that catalysts don't lower the activation energy, they provide a route with an alternative activation energy that is lower. So again, if in this case what we see is this is our uncatalyzed reaction, and here's we have our catalyzed reaction, and again the activation energy lower in the forward direction and the reverse direction are both lower, and that's why the rates of reactions are equally affected. Because if we have a lower activation energy, it's easier for the forward reaction to happen, and it's also easier for the reverse reaction to happen. So you can see here, without a catalyst, with a catalyst, you can see that the initial conditions and the equilibrium conditions are the exact same, except the only difference is that here this was slow, and here this was fast. So equilibrium is just attained a lot faster when we have a catalyst. Okay. Again, it has no effect on the reactant product concentrations. Whatever would have happened without the catalyst still happens, except it just happens faster. So again, in this case, what we see is this is our uncatalyzed reaction. Our rates are a little bit slower. Here we have a catalyzed. You can see that those instantaneous rates at the beginning are a lot faster. But outside of that, it's pretty much the same thing. You're going to get the same concentration of products to reactants, the same KEQ value, except that KEQ value is going to be achieved a lot faster. So let's take a look at here. We have this reaction here. We have SO2 plus O2 gives us SO3, and we have energy. So we can see that this reaction is going to be exothermic. Exothermic in this case because it's a thermochemical equation. The energy is as a product. So let's see what the LCP would predict if we do these following stressors. So if we added SO2, what that means is that we're adding over here. That would increase the collisions with these two reactants. Increased collisions means that equilibrium would be faster, or the rate of reaction in the forward direction would be a lot faster, and therefore what we would predict is that equilibrium would shift to the right. Now if SO3 was added, the reverse would happen, because we're going to have more collisions between here. We're increasing our concentration. That would increase the rate of the reverse reaction, and we'd see a shift of equilibrium to the left. If we remove oxygen, so we have a way of siphoning it out, whatnot, then again, what we're trying to do is that our forward direction will be a lot slower than our reverse direction, and so these SO3s would eventually create more of this. So we would see a shift to the left, so that we would recreate this oxygen and we'd also create more SO2 at the same time. Now here's the exothermic reaction, and it says cooling that reaction. So in this case, we're removing energy. So if we remove energy and we treat energy as a term, what we want to do is that we'll predict that the equilibrium will shift to produce more of that energy. Again, both of these rates would be slower, except if we're removing energy, the rate in the reverse would be a lot slower than the rate in the forward, and therefore we'd see a shift to the right. Heating the reaction has the opposite. We would increase the amount of energy that's available here. We'd see an increase in that reverse reaction, and we'd see a shift to the left. All right, F. Making the volume bigger. Okay, well, we can see that all of these are gases. So if we make the volume bigger, what that's going to do is that that's going to reduce the pressure. So if the pressure is reduced, it's going to want to increase the amount of pressure. The only way that we can do that is by increasing the number of moles. Here we have 2 moles, and here we have 2 plus 1, we have 3 moles. So what LCP is going to predict is that equilibrium is going to shift to the left to go to the side that has more moles. More moles means more pressure. So ultimately, this will shift to the left. If we make the volume smaller, well, again, that means that we're going to have more pressure. We're going to have a spike of pressure. We want to bring it back down. So the only way we can bring that back down is go to the side that has least amount of moles, and that's going to mean it's going to go to the right. What does adding a catalyst have to do with the equilibrium shift? Nothing. There's not going to be any change here. All that's going to mean is that equilibrium will be achieved a lot faster, but it won't affect the concentrations of either products or the reactants, so it has no effect whatsoever. So this is just a little summary of all the effects, the effect of the equilibrium shift and the KEQ. So if you like, you can print that out and have that in your books. Thanks very much for watching. See you soon.